So thanks all for being here today. So our work's titled Subgoal-Guided Heuristic Search with Learned Subgoals. So I'm just going to walk through a bit of an introduction, some notation, the problem definition that we're trying to solve, and then sort of walk through what are some of the new stuff that we've added to this area. So the types of problems that we're interested in are called single agent deterministic search problems. And generally, we represent this as a set of states. The agent has a set of actions available at each given state. We're looking at deterministic search problems. So there's a deterministic transition function. Once you're in a state and you apply an action, you will then get back your resulting states. The problems are usually defined as an initial state. So this is the state that we're given up front, and we're trying to reach a set of goal states. We don't generally know the total collection of goal states ahead of time. We generally assume that we have a binary function that will tell us at any given state, are we at a solution or not? And then we're using that as sort of our testing condition for when to stop our algorithms. And this will come up later, but these can be represented as sort of the underlying state space can be represented as a graph. And states are edges in the graph, and states are nodes in the graph, and an edge will join two states if there is a single action that you can apply going from one state to the next. And this is usually a directed graph because with a lot of the problems that we're looking at, the actions aren't reversible. And as the name sort of suggests, we're going to be looking at tree search algorithms. So the tree has a set of nodes. There is a special node called the root node, and this corresponds to the our starting state. Different nodes can represent the same underlying state. It's just sort of different paths and different sequences of actions that you can take to get to the various same states. And any node in the tree can be represented by a sequences of actions starting from a root. So sometimes this is helpful when we're looking at some of the ways that we represent or define some of the tools that we'll be using. And then we have a search algorithm, and generally we bound it by a budget. So there's three sort of conditions at which our algorithm will terminate. So there could be that there are no more nodes left to expand. Usually this doesn't come up with the type of problems we're looking at. There's always a way to get from the root or from the starting state to a goal state. The second is that the search incurs a loss greater than our budget. Usually this is on node expansion. So maybe we'll say that the algorithm has 1,000 iterations it's allowed to do, and then once it hits that limit, it has to stop. So that's an outcome that can happen where the search terminates, but we don't actually know what the solution was, or we were able to find the solution within our given budget, and this is by the algorithm expanding on a state that was in one of our goal collection of states. So we'll hopefully everyone's familiar with this, but a lot of the algorithms that we're looking at are variants of best first search. So we're just going to walk through an example just to show sort of the mechanism of these algorithms and how they work. So we have two queues or two lists, open and closed. So closed are all of the nodes that we've visited, and open is our sort of priority queue of nodes that we have generated, but we have not yet searched. And open is going to be sorted based on the cost. So every node is going to have an associated cost. We want to prioritize lower cost nodes over higher cost nodes. And so whenever we insert a node into our open list, we're going to be sorting it based on that cost criteria. So we always start off with the root. This is A, it's an open. And so we're going to select that as our next state to expand. So this gets moved into closed, and we're going to generate each of its children. So there's B and C. And then those go into open, sorted based on the cost here. So we have 2 and 4. What's closed generally used for is that sometimes when we're generating different nodes in our tree, they can have the same underlying state. And in a lot of these search algorithms, it really depends on what you're after. So maybe you want to have a guarantee that the solution that you find is the minimal cost path sequences of actions to get to the solution node. Sometimes we don't care about that. So one optimization you can make is when I come across a new node in my tree to add, but it has the same underlying state that I've already seen before, sometimes we're not going to include that in our tree expansion because that's just wasted effort. Because you could have a huge subtree under that node that we don't want the algorithm to waste all this time expanding. So usually what we do with our close check is before we actually add our nodes into open, we're just going to do a quick check to see, do these nodes B and C, have we already explored the underlying state that the node represents? If we've already seen this before, then there's no need to add it to closed. But in this case, we're just going to always add them into open. And then we just repeat this process. So B was the min cost node. We add that into closed. We're going to generate its children. So D and E has a cost of 3 and 5. And then C, we already had in before that had cost 4, but D was a minimal cost compared to C, so that gets added in front. So we expand D, maybe it has no children, so that just moves into closed, and then next is C, and then this process just continues. So this is just how best first search works, and depending on how we come up with the cost functions, we can generate different types of algorithms. So we want a way to sort of measure the amount of work or effort being done with our algorithms, because if an algorithm is very costly to run, this is something that maybe we want to minimize or come up with different algorithms that can reduce this cost. So every time the search expands a node, it's going to incur some loss. And then for any given node, we can ask what is the path loss. And this is just the sequences of individual losses that goes from the root to this particular node. And so if we just have a loss of, let's say, 1 for every node expansion, this would just mean that the loss that the algorithm incurs during a search is just the total number of expansions. And the types of search algorithms that we're looking at are called policy tree search algorithms. So as the name suggests, there's a policy involved somewhere. And so a policy is just a function that's going to assign probabilities to each of our nodes. And so we know that each node represents a sequence of actions. So really this policy is giving us a probability over sequences of actions. And the way that we define this is it's done recursively. So pi of n is the total path probability. And so if I have a node n and a child n prime, so it's one action to go from n to n prime, then the path probability of n prime is the parent's path probability multiplied by this conditional probability here. And so this conditional probability is what maybe you're familiar with, like a policy network. This is what this would be giving you. And then to get to the actual probability of each of these nodes, you're just sort of multiplying this for the path sequence of actions that you take from the root node until the node in the tree. And this setup is nice because we'll sort of show how this sort of works with an example. So we know that we're going to use policies in our as a way to sort of come up with these costs. And we know that best first search prioritizes lower cost nodes first, and we want to hopefully explore paths that have a higher probability. So if we're just naively coming up with a cost function, we can use 1 over pi. And if I have a high probability path, the cost of that node is going to be low. And if I have a low probability path, then the cost for that node is going to be high. So colors might be a bit hard to see, but the number inside the node is the path probability for that node. So that's pi of n. The blue on the arrows is going to be our local probabilities. So this is what maybe you get from your policy network. And to generate the value inside the node, you just multiply the blue local probabilities from the node up into the root. And then in purple here, we have the cost function. So if I'm just using the naive 1 over pi as my cost function, we can run into this problem demonstrated by this example here. So on the left and right, we have 2 subtrees, and it's a 50-50 split in terms of what the local policy tells us. And the left subtree, we just have a chain going down. It's an infinite chain. And on the right, we have an infinite binary tree. Because we're just using 1 over pi, if I have a chain going down, there's only one action to take. So it must be necessary that the local probability here is 1. And so as I go deeper and deeper into this chain, the cost is going to stay as 2 because this total path probability of each of these children nodes aren't going to change. So there's only one action to take, so I'm just multiplying by 1 all the way down. Whereas on the binary tree, because we're washing this out evenly between our 2 children, our path probabilities are going to increase as they go deeper and deeper into the tree. And so what happens here is that there'll be a point at which the costs on my right binary subtree are going to be larger than the chain probability on the left. And so if you just have a function, or if you just have an algorithm that's constantly taking the min cost node, then you're always going to be stuck in this infinite tree going down, and you'll never visit other parts of the subtree. So using just this naive cost function is a close first attempt, but it's not, we can see that there's clearly some issues here. So instead, we'll use the depth in our numerator over the path probability. And so this solves a problem where, using the same example as before, as I go deeper and deeper onto the left subtree, the numerator here, this value here, is increasing 2 to 3 to 4. And so this will bump up the costs. And it will get to the point where the costs on the left subtree will become higher than some of the options that we have in the other subtree. And so now we get this nice property where we're not going to get stuck into these infinite parts of the tree without exploring other nodes. So this brings us to the different types of policy tree search algorithms. The first is called Levin tree search. And this essentially uses what we just looked at, depth over the path probability. There's a second policy tree search algorithm called PHS, so policy-guided heuristic search. This includes the notion of a heuristic. And so when we look at Levin tree search, it's using the depth of the node and the path probability of that node. So these are all values of the current node that you're looking at. But if you're familiar with a tree search algorithm like A star, the cost function uses the path cost of that node, so G, and plus you're going to add a heuristic value, which is an estimate cost of the goal, H. So we can sort of do something similar, and this is how you can sort of think about PHS, is that G of n and pi of n are the path cost and the path probability for the node that you're looking at. But if I had an estimate cost of the goal, then what we can do is we can have an estimate depth of that goal node, which is our G plus H. And if I want an estimate path probability of that goal node, then I can sort of average the path probability that I've incurred over how deep I am in the tree. And then we can just extrapolate that out to how far I think, or how much deeper I think that goal node is. So you can sort of think about it like that. But it's just a way to include heuristic information into these policy tree search algorithms. And so this brings us to the algorithms. We're familiar with BFS now, so both of these algorithms are just calling BFS, and all we're doing is we're giving it different cost functions. So Levin tree search gives it that d over pi, and PHS gives it that with the heuristic factor included as well. So how do we train these things? The path probability will generate these using a neural networks and for our policy. And similarly, you can do the same thing with the heuristic. Now, if you had a solution database, you could just train these off of the solution trajectories, but the types of problems we're interested in, we're going to assume that they're hard enough that generating these solution data sets are a bit costly. So we can train these online using something called the bootstrap process. The way this works is just looking at, in this case, the heuristic model would follow similarly, but here in this case, we're just going to look at our policy. We'll just randomly initialize our policy. We'll take a subset of our problems, and we'll run our search algorithm, but it's constrained on a budget. This is because when we start off with a random initialized network for our policy, let's say, we don't want to give it too high of a budget because then you're just going to, your neural network, the policy values aren't really informed because you're just starting off at the beginning of training. And so you don't want to spend too much time on problems that are maybe too difficult. You want to sort of only give it a small amount of budget that can work on the easy problems, and then we can get better and better policies. So we're going to select an initial budget. We're going to run our search algorithm, and then there's 2 outcomes that can happen with the problems. Either we find solutions within our budget, and so now because I have a path probability, I can sort of look at what were the sequences of actions I took to get to the goal, how many steps away were the goal to train my heuristic, and so we can make this update And now we have a slightly stronger policy. And so we can just repeat this process. As I solve problems within my budget, we can use this to update our policy. But maybe we have very hard problems, or maybe the budget that we initially selected was too low. So if we sweep over our problems, and if we either just don't make any progress, or maybe we didn't make enough progress, we want to solve, X% of our data set every iteration, then we're not able to update our policy because there was no solutions, and update our budget. And we can just try again, give it a bit more budget until it can try and solve these problems. So that's the bootstrap process. So there's some observations here. One is that when we repeat this process, maybe we have very hard problems, and having a very large budget is not something that's that we can afford. And so you're going to be generating a whole bunch of data, all of these search trees, but we're not able to update our policy because we didn't find a solution here. So this process can be very costly, and there's a huge amount of data that we're generating that we just can't make use of because in these previous methods, I need the solution trajectory to actually update my policy. And the second is that these previous policy tree search algorithms are using a single policy model. Maybe if we get to very hard problems, it can be overburdened. And the types of problems we're looking at can generally be decomposed into subgoals or subtasks. So maybe there's a better way that we can utilize the total parameters of our model to help us with this subgoal or subtask decomposition. And just as an illustration, maybe this is the tree that we generate, and this was our solution node. So, maybe we didn't give it enough budget. We're just slightly off from finding our solution. So this entire tree would get thrown away. But maybe there's a way that we can identify some subgoals in blue here. And if we could identify some subgoals, maybe I can then start to train my policy to learn to complete different subgoals, so I can still make use of data from the tree rather than just throwing it away. So that's sort of what we'd like to do. Okay, so there's a few different contributions that we're making, and we're just gonna slowly introduce each of these one at a time. So the first is how we're going to introduce subgoals into our actual policy. So let's just pretend that we are getting subgoals somehow. So in this case, subgoals are represented as target states that we would like to get to. And what we're gonna introduce is we're gonna have two types of policies. So we have a low-level policy, and not only is this conditioned on the current state that you're in, but also the future subgoal target state that you want to reach. And so this will generate actions that are sort of conditioned on achieving that subgoal state. So if we define ahead of time, I have k subgoals, then you will have k probability distributions, one for each of these subgoals. And then I would like to combine this into a single sort of policy function, even though we're using different models to come up with these, because then we can plug and play with it with our previous search algorithms that we just looked at. And the way that we're going to do that is we're going to have a high-level policy over our subgoals. So if I have k subgoals, this will tell us what subgoal should I maybe start to look at first. And then this formula here is basically weighting all of those individual subgoal, or all of those different probability distributions that were conditioned on different subgoals. We're going to weight them depending on what our high-level policy wants to look at. And then because we end up, even though we're using multiple policy networks, because we end up with a single policy at the end of the day, we can just call our Levin tree search or our PHS, but instead of using their policy formulation, we're using our own. And just as an example, maybe I have two subgoals. I want to go left or I want to go right. And the left policy has a 95% going left, 5% going right. And then the subgoal policy for the right is just the inverse, or the flip of that. And if we just combine, maybe I don't know which subgoal to look at, so I'm just going to take each of these and equally weight them. So we could do 50-50 in terms of left versus right. You'll end up with just a uniform looking probability distribution over your actions. And so this is uninformed. The agent just doesn't know where to go. He's going to get pulled in all different directions. Whereas if our high-level policy is able to come up with, I should do left first, let's say with a weighting of 95, then we can see that the resulting policy is going to be geared towards doing that subgoal first. But there's always a bit of sort of room for all of the other actions, because there may be maybe you have a lot of the subgoals wanting you to go left versus one that wants you to go right, as an example. Okay, so that's assuming we have the sub-goal target states. So we need a way to come up with these target states. We're going to be using a model called a vector quantized VAE. If you're familiar with VAEs or autoencoders in general, it's sort of the same. It just has a slight change in terms of what we do with our internal latent state. So our encoder, it's an encoder-decoder model. Our encoder is going to take the current state and our target subgoal state. Again, we don't assume that we have this given from training. We'll show how we actually come up with these states, but the idea is now we need to introduce the notion of how do I generate these on the fly during search? Because during search, I don't know what the target subgoal states. I need a way to generate them. So this is what this model is used for. And then we'll still talk about how do we come up with these target states for training. But let's just assume that I have a current state and a target subgoal state. So this gets encoded into a continuous latent vector. And then what vector quantized VAEs do is they have a set number of possible options. This is called a codebook. So this is a codebook of size 4. And what this is going to do is it's going to take this output continuous representation and it's going to try and map it onto one of these 4 options, depending on which is the closest. So as an example, maybe my values here were 1, 4, 10, and 20. If the encoder outputs a value of 5, then it's going to look at each of these. So 1, 4, 10, and 20, and 5 is closest to 4. So we're going to take that value of 5, and it's going to get snapped and turned into a value of 4. This is nice because this will give us a way to enumerate our subgoals going into search instead of dealing with continuous representations that you normally would get with a VQ or with a VAE. And so what the decoder does is it takes our current state again, it takes in this continuous, or it takes in this codebook value, this quantized vector, and then it's going to try and reproduce our target states. And then in training, we're just trying to get the target state that we're generating to be close to this target state that we gave it at the beginning. And so just pictorially, just what's happening during search is I am at the state S, and I want to figure out what action should I be taking. So I don't know. So the encoder looks at your given state and target state. We don't have that. So we're not using the encoder. We're just using the decoder. So the decoder takes in my current state, and it takes in one of these codebook entries. If I have 4 codebook entries, then I can do this 4 separate times, 1 for each of these values. And this will give me 4 generated subgoal states. And so for each of these subgoal states, now we can plug it into our policies. So for each of these, I can generate a low-level policy. I can have a high-level policy over these subgoals. And then we can use our cost function here to then give us the cost for this node that we can then continue our search algorithm. So the VQ model during search, its goal is to give us and generate these subgoal states, but we still need a way to actually label these for training. Yep.
Thank you for drawing the picture of a little maze. Can you help me connect what a subgoal means in a maze? Is it trying to get through the hole in the wall? What would be you fill in how that maze connects to the subgoals? So,
yeah, so in this case, the agent needs to get the diamond to open up the door. And the door is blocked by, it's closed, so we need to get the key first, and then you're going to walk through, get the diamond, and then get out. So if I had a human labeled data set of what a subgoal is, I could say a subgoal is getting the key and a subgoal is walking into the room, let's say. So that could be an example of a subgoal state, the state at which the agent collects the key and the state at which the agent walks through the room. Our goal is going to be to not have to hand label those, but that would be an example of a subgoal, is the state at which the agent grabbed the key, as an example.
subgoal would be a way to say how close are you to this particular to gain the key, or how close you are to getting to the door.
So our subgoals are represented as particular grounded states. So in this case, when I want to say, give me the subgoal target state of me collecting the key, it would be the agent over the key. And then what the policy would look at is it would say, here's the current state of the agent not at the key. Here's the target state of the agent collecting the key. Then the policy would try and give us actions that are geared towards getting closer and closer to that key. And
be able to read what's going
Yeah, so that's if we're hand labeling our subgoals. So if getting the key was always a subgoal option, then we would also need some logic over top to say, don't get the key again. But if you could say, we're learning these subgoals, so hopefully that doesn't happen. During training, we're also going to be learning what was the order of subgoals I completed. So once I get the key once, if there's no second key in the room, then my subgoal policy will never see me getting the key a second time. So even though if it is an option, we could just give it a very low weight. So my subgoal, my low level policy, that's conditioned on getting the key. If the key is no longer in the room, then those are sort of garbage values because even though it's telling me to go up, down, left, or right, there is no key. So I shouldn't trust it. But hopefully the subgoal policy, the high level policy will say there's no key in the room. So we shouldn't give any weight to that low level policy because it's just going to give us garbage values.
on. Where the other situation, you are close to the key there,
Yeah.
but you know. Everybody puts the key, subgoal.
Oh, so in this case, when you get the key, it disappears from the environment, like you collect it on your person? Oh. Uh-huh.
Go and key. Subgoal. Yeah, permission.
Yeah. Okay. Yeah. So hopefully the subgoal, that could still be an option as a subgoal, but hopefully the higher level policy just doesn't put any weight onto that option. Okay, so we have a policy formulation which, given subgoal target states, here's how we can use it. We then have a formulation of generating these subgoals during search, these subgoal states using this vector quantized VAE. But in order to generate these, we had to train the model, and to train the model, I had to come up with what is the actual target state it should be training towards. So now the final piece is, how do I actually generate these pairs of current state and target state to then kickstart off this training process? So during search, you generate a tree. That tree sort of represents, so your environment has a state space graph. And we don't assume that we have the state space graph ahead of time because that could just be too large to fit in the memory. So we build a tree as we explore through the environment. And that tree is representing sort of a subgraph of the underlying state space graph. So when our search terminates, we're going to say, okay, I have this tree. Let's look at the subgraph of my state space that this represents. So we're going to call this G0. And we're going to apply this clustering algorithm called the Levi algorithm. And what this does is it's going to assign each node into its own cluster. And it's going to try and maximize this metric by moving nodes into each of the different clusters until it can't make any more progress. So you start off with the graph, and then you try and assign nodes into clusters. Once this process stops and I can't make any more progress, I can now make a new graph G1 over top. And this is where each cluster, which had a collection of states from my G0, are now represented by a single node in G1. So I'm reducing the number, I'm sort of making an abstract graph over top. And then we can repeat this process. Give each node in G1 its own cluster, try and move these nodes around as best as I can. And then I'll get G2 and then G3. And so we can continue this process up, creating these graphs. And so it's a bit small, but just as an example in terms of visually what's happening here is on the right column, I have my low level graph, my sort of base level graph. And then each column I'm seeing what states belong to what cluster as I go up into higher levels of abstraction. So at the beginning, each of these states has its own cluster. And then after I do one pass of the algorithm and I get G1, now I have multiple states that are close together are now being given the same color, which means that they're in the same cluster. And then more and more nodes are being grouped together, so I have less colors as I move left throughout my hierarchy. And the metric that this algorithm tries to maximize is it's the difference between the number of edges within a cluster to the edges between clusters. And we can think of this as we want to get really densely packed these densely packed clusters with sparse edges between the two clusters. And when we visualize sort of what's happening here is that we can see as I go up and up in abstraction, we're sort of learning different partitions of this room or the actual different rooms. In the maze, you'll get to a point where each room has its own cluster, and then groups of rooms that are connected close together has its own cluster. So you get to the very top where it's just sort of subsections of the map. And in the bottom here, we actually have a graph. We can see that it's sort of clustering around the densely connected subparts of my graph. And then between these sort of lone edges, we have our different clusters. So what this algorithm is doing is it's looking at the structure of the underlying graph, and it's trying to have the states that are close together that sort of fit this metric to be given a cluster. So this is what this process does, is it gives us a stack of graphs where we go higher and higher up in abstraction. And so what we're going to do is we're just going to pick one of these levels, let's just say the midpoint, and we're going to sample two neighboring clusters in this graph. And when we sample two clusters in this abstract graph, that's going to give us a collection of states from one cluster and a collection of states from another cluster. And then each of those collection of states, we're just going to sample one of each. And if we sort of overlay this on our underlying state space graph, this is going to give us a starting state and an end state. And then because this is a graph that we actually built during search, we know the sequence of actions that we need to take to get from one to the next. And so in this case, this is just an example where we sample and I have the states where I don't have the key. And then in this case, the sequences of actions walks over to get the key as an example. And even though I don't solve the problem, we're able to hopefully generate these clusters that are informed by interesting structures, moving between interesting structures in our state space graph. And because now I know the sequences of actions that I took for the sub-trajectory, we can now train our low-level policies, even though we didn't solve any of these problems. I can also start training my subgoal generator because I have an example of, on one end of this sample, I have the starting state, and on one end, I have the target state. So now I have pairs of target states that I learned. And because the algorithm is learning these clusters based on this connectivity, this is sort of going to generate, in this example, you would imagine that there's going to be a clusters of states inside the room and clusters of states outside the room, because there's only a single edge that can get me between these two clusters is walking through this door. So when I sample a state from the cluster from within the room, and when I sample a state from a cluster outside the room, the resulting path I'm going to get is me walking in and out of the room. So these are the types of subgoals that we're learning with these that are related to the underlying structure of my map. So when I don't solve the problem, I'm able to solve these I'm able to train the low-level policies, and I'm able to train my subgoal generator. When I do have a solution, I have a solution trajectory. And so we're going to follow a bit of a similar process. So I'm going to just segment up my trajectory. The way that we do that is when we're generating these sub-trajectories from the non-solution case, I'm tracking the sort of length, the average length of these paths. And we're going to segment this solution trajectory up to sort of be closely related to where they're the same distance for each of the sub-trajectories of the non-solution paths that we found. I can explain them more a bit if we have time after, sort of why that is the case. But so I have the solution trajectory, I segment it up. Then for each of these segments, I have my starting state, I have the target state. So that allows us to train our subgoal generator. I have the sequences of actions that I took to get from the state to the target state. So that allows me to train my low-level policies. And now I can train my high-level policy because I can see for each of these sub-trajectories, here's the target subgoal that led me towards the goal. And I can just look at my vector quantized VAE subgoal generator, and I can just look at which codebook entry did our target subgoal that we actually found during search, which one of those does it map to? And then if it maps to, let's say, the second one, then the high-level policy should learn that that second subgoal was the action that we should take going forward. So time to evaluate this setup. We have 5 different environments. Box world. So in this domain, You have pairs of colors here. So on the left is the color key that you get when you open the box, and on the right is the color key required to open the box. And then there's a special solution ending box that you have. So you basically need to come up with these sequences of keys and locks. And there's decoys. So maybe there's 2 boxes that can be opened by the blue key, but when you open up the wrong box, that gives you the wrong next key color. That consumes the key, and so now you get 2 dead ends because you went down a decoy path. Craft world, we need to sort of get these gems here, and then gems are blocked by rocks. So there's various raw materials in the environment. So you can visit different workstations, and a raw material at one workstation may give you a different tool to a different workstation. So you need to come up with these with the correct sequence of tools to make. Boulder Dash is this key and diamond environment. So we need to collect diamonds, and some of these are locked behind different doors. And the interesting part with this environment is that this brown here is sort of this dirt element. And when you walk over a dirt element, it disappears. And so the amount of states that are in these underlying state space graphs, these are very, very, very large. So these are very hard problems. Even though it's a simple finding the key and getting to the door, the search space is just very large for these problems. Sokoban, you have these goals and you need to push the box onto the goal, but you can only push, you can't pull. So if you push the box into a corner, there's no way for you to walk on the side and push it out, so you get into a deadlock. And then here we have TSP, so traveling salesman, and you have a set of cities that you have to visit, and when you walk over a city, you visit it, and then you have to return to the first city that you visited. So these are our 5 environments. So we have 2 types of problems. So our 5, we're going to sort of break up into two different classifications here. The first is these standard problems, and these are standard in that all the comparison algorithms can solve these during our online training process. So these are all trained online using the bootstrap process. And what we're curious here is what's the effort that it takes this online training process to actually solve these problems? Because the old methods, you make use of training data when you don't solve the problem, but our methods can. So here what we're looking at is during this online training bootstrap process, we're tracking how many total node expansions have we incurred. So what's our total loss in aggregate over the entire process? And then we're tracking how many problems left do I have in my training set that I haven't yet solved. And so the bootstrap training process is done when you can sort of solve all of the problems in your training set. And the methods that we're looking at, so we have Levin tree search and PHS. We have R2 variants, which uses our own policy formulation. And then we're also including WA star, which is a common comparison method in these problems. So it might be a bit hard to see, but in terms of box, so these are problems that all the other methods can reasonably solve. And so we can see here that our 2 metrics, our 2 algorithms here are below the curves of the other methods. So they're able to solve these in fewer node expansions. But there isn't too much of a gap. These problems are probably a bit too easy for these methods. And then when we look at Sokoban, there is a large grouping of these different algorithms here where there's not much in terms of gains that we can make with this setup here. And part of the reasoning or part of what we're thinking with these methods here, why you don't see either these methods are too simple, or these problem instances are too simple, or environments like Sokoban, because we're dealing with our clustering method, the way that we generate these subgoals, look at the underlying structure of the environments. If your environments don't have sub rooms, or if there's no items that you can collect that then sort of give you new parts of your state space environment, if it just looks like a soup of states like in Sokoban, then maybe the clusterings aren't really giving you too much informed subgoals here. So we don't see a large gain in terms of these sets of problems. But then we can ask ourselves, okay, during testing, are we losing anything? Okay, we don't make any gains in training. So HIPS is trained offline. It doesn't have an online way of training. It's a separate method. HIPS is very similar to PHS. The difference is that rather than searching at your sort of raw state level, like a traditional search algorithm, it generates subgoals similar to how we do using our vector quantized VAE, but it doesn't learn them on the fly. It has to be hand labeled. And the problem with HIPS is that because it's searching at a high level the search is conducted at this latent level, your subgoal generator can maybe make a mistake. It's not going to generate a state that's actually valid in your underlying graph. And so what we'll see in the next set of environments is that although HIPS has some similar ideas to what we're doing, it's going to fail when you have very hard to represent environments because it's only searching at this sort of abstract high level. And then when it thinks it finds a solution, it's going to try and ground that to see, did the states that I generate actually match to corresponding real states in the environment? And so this comparison method is going to fail when we look at some of the harder environments. But with the two environments we're looking at, we can see that WA star always tends to give the best results in terms of the solution lengths. But in terms of node expansions, at test time, our method is very competitive compared to the other two methods. So we didn't gain much in terms of training loss, but our test results are still competitive. But the really benefit of our method comes when you have very hard problems. And in this case, because again, we're learning on the online bootstrap process, whenever you don't find a solution because the problem is too hard, you can't make use of any training data for Levin tree search, for PHS, for WA star. So all of these methods are sort of flatlining because these problems are so hard where they can't really make much of any progress. Whereas with our method, because we're able to make use of data from our tree when we don't have a solution, we can sort of kickstart off this training process. And this is enough to where we can very quickly make progress and solve our training set and finish the bootstrap process. Whereas all the other methods can barely make any, they can't really solve any of these problems because it just gets too difficult. And so we set a cap of like, I think it was like 16 or 24 hours total time that it's allowed to get through the training bootstrap process. And if it can, we just cut it off because it's just taking way too long with all the other algorithms. And so, of course, because it can't really train much when we go to test time, WA star is able to solve problems on sort of our one environment, but because it wasn't really to train much, it's very large in terms of its node expansions. PHS and Levin tree search can't make any progress with the other two environments because it wasn't able to make any progress during training, whereas our method here is able to solve these very quickly. Levin tree search with our method also doesn't work great a lot of the time, and that could just be because some of these environments they benefit greatly when you have a heuristic versus when you don't. But PHS, and that's not always the case, that all environments you necessarily, sometimes Levin tree search is a bit better than PHS. It's sort of environment dependent, but at least with PHS using our problem formulation, it does very well in all of these. And then just quickly, finally, so we introduced two different things. One was our policy formulation, and one was how do we make use of training data when we don't have a solution with our search trees. So we want to know what is the contribution of each. Is there just one thing that's doing a lot of the heavy lifting? Is it the other thing? So what we're looking here is, again, the search loss during training. And red is when we have PHS. Purple is when we have PHS using our policy formulation, but we don't learn from non-solution trees. So when you don't have a solution, we'll still build the graph and figure out the metrics, but we're not going to make use of any of that training data. And then blue is when we also include that we are allowed to train from the non-solution trees. And so we can see at each step, each of the different contributions, we're reducing the total search effort required during training. So both of these sort of contributions coming up with a different policy formulation to learn different subgoals helps, as well as being able to make use of the huge amount of data that we generate during training. So that's all I have. So thanks for listening, and let me know if you have any questions.